Experiments in Physics with Dr. Frank Oppenheimer was produced in cooperation with University of Colorado Television. This is University of Colorado Television. Experiments in Physics with Dr. Frank Oppenheimer. A brief demonstration of the equipment used in the Library of Experiments in Physics, produced in cooperation with University of Colorado Television. Today's experiment
in this experiment, one can measure the oscillations, electric oscillations, which occur when a condenser discharges through an inductance, through a coil. There's a board here which provides two different sizes of condensers with the values marked on them, and one can pick whichever one wants with this banana plug, and three different coils, a fairly large one in which you can determine the number of turns by the inductance, this one in which you can count the number of turns and the dimensions, and finally a small ferrite one, or a small one with about 20 turns of copper wound around a ferrite core. In addition, one can, although there's invariably some resistance or some losses in the coil that one can't avoid, one can increase the resistance in series with the coil by varying this potentiometer here. The experiment is performed by allowing this condenser to charge up with the switch down up to the voltage of this battery of 1.5 volts. It charges through a resistor, a fairly high resistor, and then when the switch is up, the battery is disconnected and the condenser discharges through the coil. The charge leaks off, making a current which produces a field here, and one gets the oscillations. One can pick whichever coil one wants also by varying the position of this banana plug, and one can see from the leads which one is using. The voltage across the condenser as it oscillates is measured on this oscilloscope. Since it's a fairly rapid phenomena, we use the storage features of the scope. It doesn't matter particularly what amplifier one has. This is the dual trace, but any of the other amplifiers will also work. The gain is about 0.2 of a volt per division, but since one isn't very interested in the voltage calibration, one can vary the vernier to give a convenient height. On the other hand, you will be interested in the time calibration, and therefore you want to be sure that this uncalibrated light is off and that this is in the clockwise position. With the largest condenser in this coil, about 1/10 of a millisecond per division is an appropriate initial setting. One has to set the level fairly far to one side. There's internal triggering, and one uses it in the single sweep mode. We can immediately see what happens. Suppose I make this ready and look. I get a discharge, which of course I couldn't measure, but having seen it's there, I will locate the spot. That has to be done with the switch up, otherwise the battery voltage is being measured, and it'll oscillate around 0 potential. I can adjust that so it starts near one side and adjust the height of it till it's near the center, and of course get the best focus that I can on it. One wants to use the minimum intensity that will leave a trace on the scope, and of course for the higher frequencies and higher writing speeds involved, you'll need more intensity than for the lower. So now I'll erase any pattern there and put the switch down and push the ready button and try it, and I get a pattern. I can see, I can count the number of oscillations per second, or in 1 millisecond, which is about 10 divisions on the screen, and I can also see what the effect of the resistance and the other losses in the coil are. If I increase this resistance, then let me just erase half of it. You can see that there'll be a different damping. I'll put this down, make it ready, and you can see the damping is somewhat increased. The effect varies depending on the initial internal resistance of the coil. I'll put that back again. If I put an iron rod in there, I can see inside this coil here, I can see what happens again to that. Let me again just raise half of it and make it ready. And I get much higher losses, which aren't due to external resistance, but other sorts of losses. On the other hand, if I put a ferrite rod inside, I will erase just half of it. Again, make it ready. And now I have a much lower frequency. If I want to see the damping, I'll have to go to a different time scale. And I'll erase that. And I can again get the frequency and the damping. I may have to use different time scales for the two measurements. So I can tell the Q of the circuit, and I can see what the effect of different materials inside the coils are. There's some things that are worth noticing. If the time scale is much too short, if the sweep rate is much too slow, then I'll get let me erase that. I'll get a pattern that looks like that, and you can recognize what's wrong. On the other hand, if the sweep rate is much too fast, then I will get a pattern. Let's see what that looks like. That looks like that. There's the correct pattern, as you remember, looked something like that. So you can adjust the sweep rate to give a reasonable pattern. There's another precaution that one has to take. For example, if I make the level much too low, I'll erase that, then little noise then it triggers almost automatically, and a little noise in the switch triggers it, and you don't see the oscillation at all. So by increasing the level, the appropriate point, I can get the oscillation. I think these are the main precautions to take. Of course, on the very high frequency coils, let me try that one, for example, then I will need as much intensity as I can get, and let's see if I get a pattern at all that you can see on the scope. I can just barely see it. I have a little too much amplitude, but the writing speed when it's here is so great that you can't see anything, but you can see the dots which occur at the peaks, and therefore you can measure both the frequency and the damping, even though you can't follow the trace all along. Perhaps I should cut the gain down and make that just a little plainer. I'll try it once more. And now you can see the dots a little more clearly than in the first picture. And that's all that you'll be able to measure at these high speeds, but they give all the information that you need. In doing the experiment, I would try out any dielectrics and any other conductors. Here's a brass tube. You may want to have split brass tubes of different wall thicknesses. Find out what happens if you put iron or ferrite inside of these. There are a great many variations that you can try to see what the effect on the inductance and the losses are in these various coils as you do the experiment. But there are no special dangers that I can see that you will run into. That's all that is involved here.